Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Part Gandhinagar. I am the subject matter of Power System 2, which is in the 5th semester Electrical Engineering Department, and GTU subject code of the subject is 3150911. Students, we are discussing chapter number 3 of PS2, Transmission Line Modeling and Performance. This is our lecture number 10 of unit number 3, and today we are going to discuss the topic number 11. In last lecture we have discussed about the circle diagram for receiving and power circle diagram of transmission line. So in this lecture we are going to discuss the reactive compensation of the transmission line. So first of all, what do you mean by reactive power and why we need to compensate the reactive power? So reactive power is generated only when the inductive components uh, are present in the transmission system. So generally what happened, this type of component, or we can say inductive component or capacitive component, has the tendency that initially they will get charged with uh, a a particular amount of voltage and current, and once they will get charged they will get expand, and once they will get expand they release that charge in opposite to the main supply or main power. So due to this they opposes the main power, and so as the receiving and power will reduce, or receiving and voltage will reduce. So due to this reason we need to compensate the reactive power. So reactive power basically generates due to the components which are present in the transmission system. So in transmission system generally we have uh, uh, we consider R plus JX for the transmission line. So in the transmission line generally R plus JX is the resistance of transmission line itself and the reactance of the transmission line itself. So due to the line losses we need to give more input power or more input voltage or more more charges we need to transfer from the sending end side to send our desired power at the receiving side. So we need to maintain the consumer demand. For we need to maintain the consumer demands, we need to send power by including the losses in the transmission system. So that's why we need to compensate that reactive power or transmission line at optimum level, or and we can maintain the sending end to the receiving end voltage ratio. So let us discuss how we can control the reactive power in the transmission system. So here the reactive power compensation can be done with the help of like shunt compensation. So shunt compensation, the reactive power is controlled by the shunt capacitor and the shunt reactor. So first of all we will discuss the shunt reactor. So in shunt reactor, shunt means it's a parallel and reactor means it's an inductor. So to compensate the power using inductor, use the shunt reactor of the transmission line, we can control the receiving and power. Now how we why we require this shunt reactor to compensate or to control the reactive power of the system. So like it compensate the effect of the capacitance. So how this capacitance will generated, so this is the line to ground capacitance. So whenever we consider a transmission line, generally we consider two capacitance, means imaginary capacitance. First is the capacitance between the line to line, like transmission line. So transmission line itself, it's a we consider it is a plate of a capacitor, and means between two wires we have the air as a medium. So if we not keep the proper distance or adequate distance between two lines, then imaginary capacitance will be generated, or and that can harm the transmission voltage. And so as we need to maintain that distance we need to specifically maintain that distance to avoid the line to line capacitance. And second capacitance is line to ground capacitance. So in shorter overhead line may also require the shunt reactor if the line is supplied from a weak system or low short circuit capacity. So whenever this type of arrangement is there, we require the shunt reactor to compensate the power. Now light load or at no load means at the time of light load or at the time of no load, Faraday effect will cause like for the rise in the receiving end voltage that we already studied how the Faraday effect will generate. So whenever the load is not connected with the transmission line, or the load which is connected is say light load, at that time due to the charging capacitance or we can say the capacitance which is created between line to ground, the voltage will be successively increased from sending end to receiving end side. And if you measure the receiving end voltage, that will be the we can say more compared to the sending end voltage. So we need to compensate that voltage using shunt reactor. So this Faraday effect will cause a further rise into the voltage. So also this means they are unswitched type, means we cannot switch it on and switch it off, and it is connected to the bus bar without any circuit breaker or for the switching. So the shunt reactor are basically used across the capacitive loaded light lines, and that will absorb the leading VAR. So the leading VAR absorbed by the shunt reactor, and so that we can by absorbing this leading VAR the line into the line we can absorb the leading VAR, and so that we can maintain the ratio between sending end voltage to the receiving end voltage. And due to this absorption of the leading VAR, again to control the voltage across the load, means the whenever the leading VAR is present in the transmission line, we need to maintain the terminal voltage, or we can say load voltage. So by placing this shunt reactor, we can absorb that leading VAR in the transmission system, and we can maintain the terminal voltage at the load side, or we can say receiving end voltage. So the usually oil immersed magnetically shielded reactors with gapped core are used for the compensation of this leading VAR in the transmission system. Maybe we can use this short transmission as well as we can use it for the long and medium transmission also. But here what we are doing, we are compensating the effect of leading VAR. So by using such devices, we can maintain the sending end voltage and receiving end voltage ratio, so that the load terminal voltage we can maintain using such devices. Now the second is the series capacitor. So these are the utilities that we are using to compensate the power. So means to compensate the reactive power of the transmission line. So in previous case, the power due to the capacitor was present, and due to that the Faraday effect, or we can say receiving and voltage means is raised because of the capacitor was means create imaginary capacitance was created between line to ground, and so that the receiving and voltage increased due to the charging effect of the transmission line. So we need to compensate that power. So in this we are using the capacitor as a compensator, and we have connected this capacitor in the series with the transmission line. So now in this mode of compensating system, series capacitor are used to compensate the reactive power of the transmission line. How we are compensating this reactive power in the transmission line using series capacitor? uh, as we know that we consider the transmission line and its own reactance. So if we need to maintain the line impedance, we need to compensate the effect of inductive reactance. So as we indicate the transmission line with R plus jx, so x is the transmission line reactance, and if that reactance increased, or we can say due to certain levels, like certain like factors, like increasing the temperature of the conductor, or like any other else, increasing the load, the reactance of the means transmission line will increase. So we need to compensate the effect of that inductive reactance. So that we can, by compensating the effect of inductive reactance, we can compensate the we can maintain the line impedance. And if line impedance maintained, then we can maintain the sending end to receiving and voltage ratio, and also we can compensate the reactive power of the transmission line. So here the series capacitor are means we use number of capacitors as per requirement. So the series capacitors are connected in series with the transmission line to compensate for the inductive reactance of the line. And basically the inductive reactance, if we consider if we compensate the inductive reactance, then the losses which are associated with this inductor, say I square R loss. So here we are considering the reactance, so I square XL losses, and so as we by compensating that losses, we can increase the efficiency, or we can say regulation of the transmission line. Here regulation is just nothing but the difference between sending and voltage to the receiving and voltage to the receiving and voltage ratio. So it is simple, and it could be installed 15 to 30% of the cost of the installing a new line. So it is viable to use the series capacitors wherever we require, and it can provide the benefits of, say, increased system stability. So by using this series capacitor, we can reduce the line impedance, and so that the stability of the system will increase. Also it reduces the system losses. If losses are reduced, then we can have like small having means small input, we can get the desired output. So means if losses are there, then we need to send more power including the losses. So if losses are compensated using series capacitor, then we can send adequate amount of sending and voltage, so that we can receive that adequate amount of receiving and voltage at the receiving side with minimum losses. And we will get the better voltage regulation using such devices, because as we are reducing the line losses, so we can maintain the vs to vr ratio. And as the losses of the transmission line reduced due to the series capacitor, so that means that will be economic, that will become economical for the transmission company by compensating this reactive power using series capacitor. So during heavy loads, the voltage drop in series inductive reactance of transmission line is compensated. See this term, during heavy loads. So load increases, increases, so the current passes through the transmission line will increases, so that the power losses will increases. So whenever we use heavy loads, the voltage drop in the inductive reactance of the transmission line is compensated by such utility, say series capacitor. So voltage drop Vd is equal to I into XL minus XC. So here we are compensating the effect of inductive reactance using capacitive reactance. So usually 40 to 60% of the XL is compensated by series capacitor, so that we can reduce or we can increase the efficiency of the transmission line by using series capacitors. Say 40 to 60% of the efficiency we can increase of the transmission line by compensating the effect of inductive reactance. So this is the second type of compensation, series capacitor. Now let us discuss the shunt capacitor. So now in this mode of compensation of the say reactive power of the transmission line, we use shunt capacitor. So the capacitor which compensate the line reactance is connected in this mode of compensation in parallel with the transmission line. So here you can see the setup. This is the transmission line. We consider R plus JXL. This is the sending end voltage Vs. This is the generator. After this we have the transmission line, and this is the receiving end voltage, and this is the voltage. In between we have the capacitor, means XC is connected, and this is the shunt capacitor which is connected with the transmission line to compensate the reactive power of the transmission line. So basically it supplies the reactive power and boosts the voltage of the transmission line. So capacitors are used throughout the system and are applied in a wide range of size. So by injecting the reactive power into the transmission line, we can compensate the reactive power of the transmission line. Here we are injecting the capacitive capacitive means reactance in this so that we are injecting the capacitive leading say I square XL. We have the losses of the due to the transmission line is I square XL, and here we are using the shunt capacitor, means they are installed near to the load terminal at the receiving and substation. And generally in switching substation, most of the industrial loads, say induction motor and then welding furnace and the air condenser, so these are the heavy inductive loads, and this loads draw the large inductive current of say poor power factor, and by keeping this much amount of power factor, this devices will work properly. So we need to if we need to improve this power factor of this devices, means say zero point 0.6 and 0.7 lagging, thereby we need to IXL, means IXL drop in the line is reduced, and the voltage regulation is improved. So by using such devices, the power factor of this line will reduce, and we need to compensate that power. So we use the shunt capacitor, and we can inject the reactive power to compensate the effect of the power factor of the transmission line. And as the power factor of the transmission line maintained, then automatically we can reduce the drops or losses inside the transmission line due to the inductive reactance. And the capacitors are mainly connected either to a bus bar or through a tertiary winding of the main transformer. So by using this capacitor as we use this capacitor at the bus bar and at the tertiary winding of the, by using the capacitor at the bus bar and the tertiary winding, we can reduce the effect of the inductive reactance at the load terminal of the transmission system. And the shunt capacitors are also used in distribution system for power factor correction. So if we place this shunt capacitor bank wherever we require, so we can increase the power factor of the transmission line and power factor correction of the feeder. So as the feeder power factor corrected, then we can increase the feeder voltage, and we can have the access and we can have the control on the feeder voltage by using shunt capacitor. So wherever the we require this type of capacitor banks, we can use to compensate the line reactance, as well as the at the load side we can improve the power factor of the system, so that the reactive power is compensated, and we can improve the efficiency and regulation of the transmission line. The power factor correction is provide this reactive power close to the point where it's being consumed rather than supply. So it from like remote sources. So wherever the remote sources are there, we can use this capacitor bank to maintain the reactive power of the transmission line. And this shunt capacitor are used to compensate the effect of I square XL losses in transmission line system, and to ensure the better level during the heavy loading condition. So whenever such type of setup we use, we can improve the power factor, as well as the we can reduce the losses of transmission lines, say I square XL losses, and we can improve the power of the means the ratio between sending and voltage to the receiving and voltage, and we can improve the regulation of the transmission line by using this capacitor banks in the transmission line. So after this topic, you have the assignment question. The assignment question is explain method of reactive power compensation with suitable line diagram. Student, this is the last lecture of this chapter number 3. So this is the instruction which is related to this assignment question. Please read it carefully and submit your assignments within time. If you have any query or any doubt, we can solve your queries and doubt related to this topic in our solving session. Also feel free to call me anytime to solve your doubts related to the any of the topic of the electrical engineering. And after this we will discuss the chapter number 2 of this power system 2. So this is the last lecture for this chapter number 3, and you can take the snap of this assignment question slide. So thank you very much, student. Thank you all. Jai Swaminarayan.